Good morning and good afternoon. Hi everyone, and thanks for joining us today on our very special webinar, Optimizing Sputtered Thin Film Alloys. My name is Diane Garver, and I will be your moderator for today's session. Before I introduce our presenters, I want to let you know that we are recording today's session, as well as taking your questions. So just enter your question on the GoToWebinar panel during the session, and we'll answer as many of your questions that we have time for. At the end of the webinar, we're happy to connect with you to answer any additional questions and discuss some topics in more depth that you may have. Joining us today is Dr. Dan Marx, VEM's Technical Director, as well as Siddhi Sanjawala, who is representing VEM's Engineering Department. We're very excited to have all of you here, so let's get started by taking a look at today's agenda. As noted, Dan and Siddhi will be discussing optimizing sputtered thin film alloys. They'll be addressing how to tailor thin film alloys to meet device requirements, how to utilize alloying to stabilize properties, and how to develop new alloy films for new devices. For the most part, we'll be addressing your questions at the end of the session. So with that, thanks again so much all of you for joining us, and I hand this off to Dan and Siddhi.
Thank you, Diane, and welcome everybody to the webinar this morning. What I would like to do is to illustrate issues faced by thin film engineers as they're developing new devices and moving their technology forward, and how that translates into the challenges for the sputtered target materials engineers, the guys making the sputtering targets. We will all employ material science, including chemistry, physics, and engineering. And I want to emphasize that communication and cooperation between the user and the producer of thin film source materials, the sputtering targets, is a key to success.
So Dan, a couple of my customers ask a few key questions. The first being, I can't light my plasma. What can I do?
And immediately, as a thin film, as a sputtered target materials engineer, I'm automatically thinking about what is the nature of the material that's being sputtered. Is it conductive? Is it an oxide? Is it a metal, suboxide, etc.? If it's a magnetic material, my mind is automatically going toward understanding how the thermal-mechanical processing may impact the magnetic properties of a target.
The next question is, my film chemistry is off. Say I wanted a tungsten tie with 10% weight titanium and 7% weight tungsten, but it's not coming out how I want it on my film. What do I do?
And that's where we, as a sputter target materials engineer, will be thinking, what is the interaction between the elements in that sputtering target and their interaction with the plasma?
Next question is, I want my films to do something new. Can you help me with that?
Wow, and that's where it really becomes a challenge for the target engineer. First questions are, what is the material? What does the phase diagram look like? Is there a phase diagram? And it also points us into the direction of needing to do background research and figure out whether or not we need to develop new processes to make those materials to meet the thin film engineer's requirements.
Finally, my films aren't performing the way I want them to. Is there anything you know how I can do that?
Yes, by looking at the types of films that you, the engineer, are using as for thin film applications, it's our job to understand what additions or what alloy additions will help solve the performance without changing the overall performance of the basic alloy. And I'll go into this some more as we go forward. So let's see if we can help. I think the first thing we need to address is, what is an alloy? And then we'll talk about the properties that need to be controlled, the need to design alloys to meet those properties, and then what it takes to manufacture those materials in a form that lends itself to high volume manufacturing. And this is where vacuum engineering, for instance, comes in as your ally or your partner in this development. Excuse me. In the simplest form, An alloy is the intentional combination of two or more elements, one of which is a metal. Some of the most common alloys that we all encounter is, for instance, steel, which is an iron-carbon combination. Stainless steel is iron and chrome, or iron, chrome, and nickel. Commonly in the thin film area, we encounter resistor materials such as nichrome. This is a nickel-chrome alloy. And in barrier materials, they mentioned the tungsten titanium alloy, which again, we have developed these types of combination of metals to produce materials that will serve as barriers to interdiffusion. Other alloys may actually incorporate ceramic materials. I include this in the whole area of what are termed cermets. The hard drive industry in the data storage world uses a whole host of cobalt platinum plus oxide type materials. These oxides may be as high as 30 or 40 volume % in that material. Again, the challenge is to use these materials to produce thin film that produce desired results, and on the target manufacturing side, the question is, how do I make them? And finally, ceramics. I put alloys in question. Is it really is it a metal or is it an oxide type material? But in any event, the most common one that many people encounter is indium tin oxide for use in transparent conductive oxides. Another material seeing more interest in developing wireless applications, for instance, the barium strontium titanate plus the addition of transition metals lead to the development of variable capacitive materials. But again, you can see that all of this is a combination of metals and other elements. So what properties do you want to control? And this is, again, from the thin film engineer. They may want to be controlling interdiffusion, film resistivity, contact resistance, electromigration, the crystal parameters, the crystal lattice structure. Smart materials are gaining much, much more attention these days, such as piezoelectric, magneto-optic, thermoelectric, and I can go on with many different types of smart films. In the magnetic area, people want to control in their thin films the magnetic coercivity, the saturation, etc., for both the media and the thin film head. At the same time, controlling those properties, the thin film engineer needs to be sure that the source material can be sputtered. And really the challenge there is, if it's a magnetic material, how do I make it less magnetic so I can sputter it? If it's a conductive material or a non-conductive material, I need to be able to think about how I can take a non-conductive oxide material, for instance, and make it conductive enough to sputter using some of the various rectifications. And at the same time, as the thin film engineer goes from development into production, they're looking for efficient use of their materials or better material utilization. So an example really to illustrate how alloy development over the years has gone into the improvement of semiconductor device performance. I may take a step back in time, but looking at as aluminum as the interconnect material. Years ago, our industry started out with putting aluminum directly on top of silicon. However, if you look at the insert of the section of the phase diagram, which is the aluminum-rich side of the aluminum-silicon phase diagram, and typically the thermal budget in semiconductor processing may be on the order of 450 degrees C. So if you look where the 450 degrees C line crosses the aluminum solubility, the silicon in aluminum solubility line, you see at 450 degrees that aluminum can dissolve up to 0.5% silicon. This leads to problems of interdiffusion with the silicon dissolving into the aluminum, producing a failure called junction spiking. So in order to minimize that problem or eliminate that problem, the thought was, how about if we supersaturate the aluminum? And by supersaturating it, if you put 1% by weight silicon, you won't have this problem, though you will eliminate the desire for that interdiffusion to occur because you've supersaturated and the chemical driving force is no longer there. So this is where the aluminum 1% silicon alloy was developed. And then as the technology has progressed, what we find is the current densities, the amount of electrons going down a circuit path, becomes ever increasingly higher. Today, well above 10 to the 6 amps per square centimeter. When you're flowing that much electricity down a very fine conductor, you end up getting, not only do the electrons flow, but you get a net flow of the atoms in that line, leading to the problem of electron migration. To solve this problem, the semiconductor industry developed the aluminum copper alloys. And what they're making use of is the fact that aluminum copper will form into metallic compounds that will form in grain boundaries, minimizing the ability for the elements in that, or the aluminum in that trace, to actually migrate. In the copper metallization world, people are starting to add manganese for the exact same reason, to minimize electron migration. But if I go back up to that aluminum silicon phase diagram, you also see that at room temperature, the solubility of silicon in aluminum is very low. And what does this lead to? It leads to the formation, and when the device goes back to room temperature, leads to the formation of silicon precipitates in contact windows. So what the industry said is, well, if I can control the electron migration, what if I put a barrier between the aluminum and the aluminum copper, and then I can eliminate the problem of the silicon junction spiking and the precipitation of silicon in contact windows. So this is where we then moved into the barrier technology. And one of the more common alloys for barrier technology is the tungsten 10 weight percent titanium alloy. This often is sputtered with nitrogen and is typically used in aluminum metallization. Titanium sputtered reactively with nitrogen produces a titanium nitride alloy, which is used for both aluminum and copper metallization. Tantalum, also sputtered reactively with nitrogen to form tantalum nitride, is the barrier of choice for copper metallization. Now you've got tantalum or tungsten in direct contact with silicon and in direct contact with the aluminum metallization. And the challenge here is, how do I reduce the contact resistance between, let's say, tungsten and silicon and tungsten and aluminum? And therein, the industry has moved to the development of metal silicides. These are things like tungsten plus silicon, tantalum silicide, moly silicide, to reduce contact resistance. Furthermore, we've moved further along to the use of what are called self-aligned silicides or salicides. And here people use titanium, cobalt, nickel, platinum, and in most advanced applications, again, we're looking at an alloy of nickel plus cobalt. Alloys play a very active role in the performance of resistors, whether it's an embedded device, whether it's a discrete device, or it's being sputtered on a ceramic for hybrid circuitry. So the first choice of the thin film engineer is, which of the alloys that are used for resistors should I choose? And what you can see from the table here is you get a fairly wide range of resistivity in microohm centimeters or sheet resistance in ohms per square. And you can see, as a function of your selection of alloys, you can fall into different regimes of resistivity and then tailor that. Again, the graph on the right side illustrates how film thickness impacts sheet resistance. And so again, if you've got the resistivity microohm centimeters to dial in a certain sheet resistance, you end up optimizing film thickness. But again, so now not only do you have a resistor, but you want to control those resistor properties. And here's where alloying comes into play. And later on, I will show an illustrative example of the additions of, say, silicon or aluminum to nichrome to reduce that thermal coefficient of resistivity, or TCR. Alloys play a very, very large role in the performance of today's data storage, hard drives, and thin film heads. Today's hard drive media may have upwards of 10 to 15 or more layers of metals and alloys. In the graphic at the top right, if you look closely at it, you see certain layers, seed layers, growth layers, and oxide segregated magnetic layers. And the key here is all of those specific layers, if you look at the words in there, they're all in plural. So not only do you have a seed layer, but it may be multiple layers making that seed layer. And the challenge here, and one of the key challenges here, is the growth underlayer, which the concept here is to produce a material that enhances the directionality of the growth of that magnetic storage layer, the cobalt platinum or the oxide segregated layer. And what people have done, that growth layer many times will be ruthenium. And with the addition of elements, other elements to the ruthenium to make a ruthenium alloy, you can control the lattice spacing of that ruthenium alloy so that the cobalt alloy that's being deposited directly on top of it will undergo and will deposit and grow with that same orientation, so that you get a very highly oriented film. And this is what's often called heteroepitaxy. Another area for alloy development is in today's media. You're sputtering a cobalt alloy, it may be cobalt, or it may be iron plus platinum plus an oxide, or maybe even carbide material. And when that deposits, what you end up getting, if you look at that picture, you get many gray and black, between gray to black little round dots. Each one of those is a metallic grain. The white surrounding that is either an oxide or a carbide type material. And what that does is help delineate each one of those grains for better individual grains with specific orientation. And so the challenge of the thin film engineer in the data storage is how few of those bits can I put in one area to create a single bit, or how few of those grains can I put in one area to create a single bit. And today, this may be anywhere from 5 to 10 of those grains will produce one bit. So again, the challenge is you've got the isolation of the grains by adding the oxide, and then it's a choice of which metals you use in developing the right magnetic properties. So the challenge, so now the thin film engineer may be doing their development. Many times they'll take a target and they'll put little pieces of other metals on top of that to co-sputter and produce an alloy. Alternatively, they may have an R&D machine that has 2 or 3 cathodes that they can co-sputter. But neither of these approaches lend themselves to high volume manufacturing. So the thin film engineer may have finally identified what is the composition of the film they're looking for. Now he's also challenged with, I want to go into volume production. So then the thin film engineer needs a material source for his deposition that is structurally uniform, compositionally correct, reliable, repeatable, and low cost. These are the challenges that the sputter target engineer is facing to satisfy the thin film engineer's requirements. So as Cynthia mentioned earlier in the talk here, the first question is, I want a certain alloy, but can I sputter it? And so the question is it a conductive material? Metals and alloys are typically conductive and not really posing a challenge. Magnetic materials, if they're a metal or an alloy, yes, they're going to be conductive, but if you're doing magnetron sputtering, the problem is the magnetic nature of these materials may prevent the magnetic flux from escaping above the target so that you can maintain the plasma. So the question then is, what kind of thermomechanical processing do I need to do to these magnetic alloys to make the magnetic properties less so that I can get some of that magnetic flux from the magnets behind the target to go through the target and enable you to maintain a magnetron plasma. If it's a non-conducting material, typically you're relegated to using RF rectification. But there's also this whole realm of somewhere in between conductive and non-conductive, and I kind of put this in the area of suboxide targets. One of the most common suboxide targets that people encounter is the indium tin oxide. In stoichiometric indium tin oxide is generally a yellow or a yellow-green type material. Yet common target materials are black or gray. And this is indicative of a suboxide type material that is sputterable. Another example, titanium dioxide. The one example I'm referring to utilizes a titanium, not TiO2, but Ti 1.8. The oxygen deficiency in that enables to improve the electrical conductivity sufficient so that you don't have to use RF rectification, but you can use DC, pulse DC, or AC type rectification. However, if you're trying to get a TiO2 film, you're still going to need to bleed in a reactive gas such as oxygen to get a stoichiometric film. Another question that I come across fairly often is the question of, gee, I've asked for a specific alloy, you made the target of that specific alloy, but the composition isn't correct. One of the most common examples of this is sputtering with tungsten titanium. The industry typically will use a tungsten 10 weight% titanium film. However, the film generally will have 7 or less weight% titanium in it. What's going on? Well, if you simply look at the difference in the mass of the titanium and the mass of the tungsten as they collide with the argon atoms in the plasma, the tungsten colliding with the argon atom will tend to continue straight on directly to the substrate. Or if it scatters, it'll scatter at a much lower angle than colliding titanium and argon, which will scatter in a much wider direction. We also see this phenomenon occurring when trying to sputter alloys such as aluminum scandium or lead zirconium titanate, PZT. Very often you have to optimize the target chemistry to match the substrate film chemistry. Controlling the alloy film, as I mentioned earlier, just if we look at resistor films, not only do you want to get a specific resistivity in your film, but that resistivity will change as a function of temperature. And so another one of the challenges of the thin film engineer is to control that variation, to control that change in resistivity as a function of temperature. And purity may not be the best answer. I know I was involved in a previous life where we were supplying very, very pure nickel chrome alloys. But the phone rings and the customer says, my films aren't performing the way I want them to. And in the table on the right there is a very good example of that, where you see a nickel chrome 40 as cast as a TCR, thermal coefficient of resistivity, of 93. As sputtered, that TCR is actually even a little bit larger at 112 ppm per degree centigrade. And even worse, with a high purity nickel chrome, you see that number jumps as high as 150. Looking down that, with the additions of essentially what we're doing is intentionally adding aluminum to that nickel chrome alloy to intentionally make the material effectively less pure. And you see, as a function of the amount of aluminum that that have been added to the nickel chrome alloy, you see that the thermal coefficient of resistivity can be dropped down into single digits. So again, it's the kind of idea of understanding what it is that we can do with the target material that helps the thin film engineer control the properties that they're trying to control in their devices. One question that simply did not raise was this question of, gee, now that I'm trying to get, I understand the chemistry, I now have a sputter target that will give me the film that I'm looking for. Now I want it to last a long time because I'm going into volume production. And one example of this is sputtering nickel. And nickel, as we all know, it's a magnetic material. But if I look at the phase diagram and I see that curved line down at the bottom left-hand side, and you see it says magnetic transition or transformation, and the key here is if I use a nickel alloy in which I've added, let's say in one case here, 7 weight percent vanadium, it no longer is sitting at room temperature in the magnetic regime. And so now I've got a sputtering target that can produce a nickel film that actually etches very similar to a pure nickel film that is non-magnetic. And instead of being limited to a nickel target, magnetic nickel target that may only be 3 millimeters thick or maybe 1/8 of an inch, 0.125 inches thick, I can make nickel targets containing 7 weight percent vanadium as thick as 1/2 an inch or more, thereby allowing the engineer, the thin film engineer, to be able to use this target in high volume manufacturing, minimizing the number of times they have to do a target change. Obviously, target changes reduce productivity. And then finally, the most serious challenge for both the thin film engineer and the sputter target engineer is the front. I want my films to do something new. And so we work with the thin film engineer as they are starting to develop a new alloy system or CERMET system. And then the question is, when we identify that, the sputter target engineer is going to be thinking, first of all, what is this material? How do I process it? Is there a phase diagram? How can I conduct a compositional field survey to test what is the right combination of the alloys that gives me exactly what I'm trying to do? Oftentimes, the request is for very dissimilar materials that don't necessarily want to be blended together. The question then is, how can I put these together in a form that produces a coherent, solid target? Another question, as I alluded to in the data storage industry, is how can I consolidate alloys and ceramics, CERMETs, into, again, a solid coherent target? And finally, how can I make it sputterable? If the request is an oxide type material, we can, through processing of the bulk materials, produce what are called suboxides. And this is very often done in the area of what are called mixed metal oxides, ITO, indium tin oxide, PZT, lead zirconium titanate, BST, barium strontium titanate, and others. So now the question is, the thin film engineer has identified the composition of the film they want. They've identified the properties of that film. The question then comes to the people who are producing that source material for the thin film engineer. You know, the question is, how do I make it? Making a 2-inch diameter target is much different than making a target that may be 16 inches in diameter. Therein lies the challenge. So do I go down the route of melt and cast, or do I go down a parallel route of using powder metallurgy? For the sake of this discussion, I want to focus on where powder metallurgy comes into play. Here you're controlling solid-solid interactions, you're making use of thermodynamics, and then the selection is of the various sorts of consolidation techniques using things like inert gas hot pressing, vacuum hot pressing, hot isostatic pressing, or HIP, or spark source sintering, SPS. And where powder metallurgy really comes into play is it enables the production of sputtering targets that blend elements, alloys, and oxides into something that can be used in high volume production. At the same time, powder metallurgy enables the thin film engineer to get a series of development alloys, adjusting composition, or as I called it, a compositional survey. And you can do this very easily using powder metallurgy by just changing the blend that you're putting together. Powder metallurgy is all about solid-solid interactions. And through the proper selection of your processes, you can control those solid-solid interactions. And really a good example of that is in the area of tungsten-titanium, the tungsten-titanium alloy. Herein, as a function of temperature, time, and pressure, we want to control the formation of what's called beta-ti tungsten. It may be a little difficult to see, but if you look closely at the picture on the left, and that center particle is a titanium particle, but what you see in that picture is a lamellar type structure. And this is the result of tungsten dissolving into titanium, and then as that consolidated material returns down to room temperature, you end up precipitating a tungsten-rich area within that titanium particle. The problem is that when you sputter, the sputtering process tends to undercut that lamellar structure, leading to it breaking off and leading to the generation of particles in the film. Again, as I said, if I control time and temperature and pressure, I can actually produce that same alloy, eliminating the issue of this beta-ti tungsten formation. Another area where powder metallurgy comes into is in the use of or the production of alloys that have very reactive metals, such as titanium and aluminum. And the picture on the right is an example of a consolidation where you see titanium particles, which are the light particles. The light gray regime is actually a titanium aluminum intermetallic, and what you can see in the darker gray area is residual aluminum. And so again, depending on where I want to be in the sputtering process, I can tailor from a blend of almost all elements to a combination of elements and metallic. And again, if I go all the way a long time at temperature, I may convert all of that to a single intermetallic phase. So again, powder metallurgy enables you to control the degrees of each type of phase being formed in your target material. Cermets, again, for the data storage industry, is key to advanced storage applications. The challenge here is combining various different materials. It may be metals, oxides, alloys of metals plus oxide. And they all have different shapes and sizes. And what you can see as you improve your powder preparation and consolidation techniques, you can go from a rather non-homogeneous structure shown in generation 1 through to a very uniform fine structure as in generation 3. And again, this comes into how you treat the powders that are being used to generate your sputtering target. Powder metallurgy, another application, is in the thin film packaging or flip chip packaging, for instance. Chrome copper has been used as an underbump metallurgy. Chrome and copper do not lend themselves to a melt and cast. You can see the wide variation in the melting point from the phase diagram. So what can we do? So if I want a chrome copper target, I can use powder metallurgy, taking copper and chrome, blending them, the copper being soft, and through the pressing process, we will actually encapsulate the chrome, making for a high density, high performance sputtering target material. So as you can see, what I've tried to point out here is the need for the thin film engineer to work with the thin film source material supplier. At Vacuum Engineering, this is exactly what we do. Our engineering team, our engineers have more than 25 years experience each. in the area of target development and target manufacturing. We employ a high-powered, high-temperature vacuum hot press. We've got blending capabilities, various different methodologies, so that you can produce a uniform microstructure in the target material. Bonding, obviously many of these materials will be bonded to a backing plate, whether it's diffusion bonding or solder bonding, and being able to check those bonding capabilities using ultrasonic C-scan technology. So basically what I've tried to illustrate in a brief seminar here is a generation of the understanding of that it's the thin film engineer who's trying to create a new device. Their challenge is to identify what alloy will produce the film properties that they're looking for. They want to be able to do that in high volume production. And it's the challenge of the Sputtered target engineer to understand what it is that the thin film metallization engineer wants and transition that into producing a bulk target material that enables that device to be produced in volume. I believe that the key to this whole thing is communication and cooperation between the two engineers, the thin film and the Sputtered target engineers. Those are the keys to success. Right?
So as we come to the close, I'll turn it back to Cynthia and open it up for some of the questions that you've been receiving online.
Yeah, thanks. So the first question is, what about, do you have any suggestions for sputtering nickel copper with a higher percent composition of copper?
Well, one of the things, I don't think you're going to run into the problem of a film chemistry variation because nickel and copper are so close to each other in atomic mass. That I would almost expect that if you had a copper nickel, you said with a high copper content, yeah, a copper nickel alloy would be virtually one-to-one in terms of what's in the target versus what's in the thin film.
Okay, thank you. The next question is, I'm sputtering with a pure aluminum target, and after the plasma starts, it is stable. But while getting the plasma to start, there's generally electrical arcing on the aluminum target. The target is about halfway through its lifetime compared to other targets they're using. This only happens with aluminum.
Well,
is it due to an uneven surface of the aluminum target, or could it be something else?
Without much more information than that, one of the things I immediately think about is what is the purity of that aluminum that you're sputtering? Oftentimes, arcing is a phenomenon that occurs when there is a contaminant or an oxide included in that material. And oxides or contaminants are sources for arcing and micro-arcing to occur. So what we would really need to do is explore further what you're doing with your sputtering target, and we can take that offline.
All right, thanks, Dan. Next, are there any advantages for depositing an alloyed target over co-sputtering?
Oh, yes. Well, as I mentioned earlier on, co-sputtering or co-sputtering by virtue of having two different cathodes, or co-sputtering by virtue of putting a second metal on the face of your sputtering target. These are processes that are generally used in research and development. But once the alloy is actually identified, or the alloy in the film is identified, you really want to be looking at systems where I can get a single target that has the composition, when it is sputtered, produces the right composition on your thin film.
Well, that's great, Dan and Sissy. Thank you so much. We'll be following up with everyone today, making sure that you have a recording for this session. And please feel free to reach out to any of us if you have questions. Dan and Sissy's information is listed here. They both can be reached at the same phone number. And thank you, Dan and Sissy, for your time and expertise. And thank you all for attending this webinar. We hope to see you on a future webinar, and have a wonderful day. Thank you very much.